Right. So at least we have two parts for the recording. Okay. So with regards to data encapsulation, it's mainly how information gets encapsulated in that container, as I explained to you earlier, and that you saw in the analogy of how information gets, saved. So we normally would, from the sender, which is obviously in this case Huawei.com. The data gets sent, which is maybe a piece of the website that you want to access or a file that you wanted to download. That all gets stored as data. And so that's on the application layer side. What happens on that part from the data, because application layer is now three layers. Remember your OSI layer, we've combined session layer, application layer, and the what's the other layer? Let me just go back. The presentation layer. So we've combined that all together to create it called the application layer. And so from there it goes down to layer 4, which is now your transport layer, right? That's layer 4. So what happens on layer 4 is that all your packets, now your data and all of that, gets broken down into segments, right? Smaller little segments, right? Before it gets sent. That segments each contain a source and destination port, right? So it has the TCP header. So the TCP header from transport layer deals with ports. So whatever port it was, let's say it's Huawei.com, so that would be port 443, which is secure, and then you would have the random port which actually requested the space, which would be I don't know, any other port number that's there, but that I'm just putting it there to say that's the server port information, which is obviously the sender. And then when you look at it, that information, all of that gets then chunked into a header. That header has a lot of information in there. And as it goes to the next layer, which now is layer 3, you then have that added as part of the payload. So from the data, that becomes the payload. And then that payload now have the TCP header information. Network layer here, layer 3 here, gets the IP address of the destination. It also has the port already because it got that information because that's part of the TCP header. And also it adds more other information to it also. Then after that, it then becomes, the next layer's payload. So then the IP header information is there. It gets added together, right? So it adds a payload, and that then it goes down to the layer 2. So I have layer 2. So at layer 2, there's some error checking there on the frame because you're dealing with frames here. Here you're dealing with a packet. And that checking there basically now gets added as a payload. So in your payload, you basically have your TCP header, your IP header, as well as the data. So all of that all is part of that payload on layer 2. And then the Ethernet header basically then adds its value. So now remember you deal with MAC address here on layer 2. So they add the source and destination MAC address and other information that goes in there. And that gets converted to bits, so ones and zeros. So that gets converted and it gets sent on a physical layer through either Wi-Fi, through either the network cable, through either fiber or satellite. Right. That's the encapsulation part now from a sending server to your PC. So the information still gets sent. Now, when you look at how it works on the devices on the network, you have the server here. So this is the web. Let's call it the web server. And so the web server then again works on application layer because remember that's the top layer. As it goes down, as it's now basically encapsulated and it gets to the physical link layer, it goes through the network. And remember that's ones and zeros here. So that's binary. It gets up the physical layer and to the data link layer. And why we say data link layer? Because it's layer 2 and your switch operates on layer 2, right? So again here, it looks at information in the source destination, sorry. And then after it find out, oh, okay, now I know what's the source MAC address that it needs to go to, it then sends information to the router. Now, the router will basically do this whole de-encapsulation again. It will remove the source and destination information. It will remove the destination MAC address. But then it gets to the network layer. Again, it says, oh, now I have got that information still encapsulated. So on layer 3, it then obviously now understand what's the destination IP address that it needs to go to and what's the source IP address, which is the server where it's coming from. And what it does is it does its encapsulation again with all that information, and then it sends it to the PC where it received it from. Uh, I think this is no, I think it's wrong. This would be the client, sorry, because that's a client, because that's a PC or laptop, and this would be the server. Right. So that's a server. So what happens is that client-server relationship, the same story, just the other way around. So again, you now have exposing the data from the data link layer, dropping the header there, dropping the header there, dropping the header there, and then you only see the data, which is obviously server data that's seen on the PC. And that's how you see websites and things like that. So that basically just explaining you how the whole encapsulation works, when you look at this exarium. Now let's look at the de-encapsulation. We've seen now what happens when you encapsulate data. And so when you de-encapsulate, and this is what I showed you slowly, you have a web server, and obviously the client is somewhere in the side, but the web server again, what it will do is it will receive that data as it goes up, and all of the headers, so the Ethernet header on layer 2 will be dropped. So that will be dropped, and you will only have the payload. In that payload, remember we have the IP header of the router. So that goes up, and then they will take the header away from that payload, and the IP header will fall away. That's the de-encapsulation. Then you go up again. Now in the payload here, it's still TCP. So it goes up the layer, and then TCP will fall away because now you're at layer 2. And then TCP then will just forward the data as a segment to the application layer, and that's how you'll see the web page. So that's the whole encapsulation part where everything just gets removed in that sense. And that is basically how it works on the network devices. So, so what you would also see is that there would be these protocols, and so these protocols again, they operate in different layers, right? So you have the data link layer that deals with the Ethernet protocol, and the PPPP, which you saw earlier in packet in Wiresock. Then you obviously have the network layer, which deals with IP, and you have ICMP, which basically is their service to send pings. So ICMP is a protocol that allows you to send pings. And then you have the group IGMP. And the transport layer only deals with two protocols. You have TCP and UDP. And then your top layer deals with different type of protocols that you get use of. So you can see all these applications that we use, DNS, DHCP, HTTP, they all use the application layer as part of that. Now, when you want to understand how this works on the other layers, TCP, these would have port numbers, and so TLN would have a port number, HTTP would have port 80, or HTTPS, if there's an S, then it's 443. If it's FTP, it's normally port 21. And if it's SMTP, I think I can't know, I don't know what that port is, but TLN is also port 21. DNS is, I think it's 53. DHCP also has a random port that they normally use. These are just the ports, but what you can see basically is the ports labeled the transport layer, and how information gets sent. Now, TCP has a header, and this is basically what the header looks like. The header basically is, the following. So you have, these information that's in there. TCP is a connection-oriented protocol, so it means that it maintains that there's a connection, but you have the source and destination port, and then TCP deals with acknowledgement numbers and sequence numbers. So what it means is that as the packet or as the segment, and I'll just show you that in Wiresock. Which Wiresock now? Okay, there we go. So if you see earlier, I used UDP traffic, right? Let's see if there's any TCP traffic here. TCP, there is some TCP traffic. So if you look at it, I'm going to open up this one, that's application data. So you can see basically here, let me just see, yeah. You can see here basically you have the frame, which again is the layer 2. Let me just try to minimize that so you can just see it from this side. And then under TCP, you have your transport control protocol. So you can see if I drop down this, there's the source port, which is 443, which is a web server. and then that is a random destination port, which kind of the web server is responding to my PC and sending data back. So the source port is the server sending to my random port on my PC, and here you can see the segment, and here's the sequence numbers. So the sequence number is basically what's the next sequence of the segment that goes out, because it send it all in sequence, in segments and sequences. And then there's the sequence number also. What's the next one? So you can see there's 10548. The next sequence is 10586. And then there's always obviously a relative acknowledgement number. These are all information that's in the TCP header, and this is how the devices known about each other on the network and how you would send information over the internet. So that's TCP. Now, when we look at UDP, smaller table, not much information. So with UDP, you have let's say I've got a lot of UDP traffic, so I'll just do that. So there's UDP again. So with UDP, you have, just minimize that. You have your UDP traffic here, user datagram protocol. So you have your source port, which in this case could be their UDP port, and then its destination port again could be my PC's port, depending on, I'm not sure where this is coming from. But that information you can see at the bottom is your source port, and destination port. What the 16 means is just the bytes, the amount of bytes for these values. And then you also have a length, as you can see there, and then a checksum value to just check, was this, because UDP doesn't care if you drop, if any information is dropped. It's connectionless, doesn't care. But that's why you guys can see that we're doing the streaming now. And if I just play this again, while I'm sharing my screen, you will see it's mostly UDP traffic. Right. Now, when we look at the following, which is UDP and TCP, the comparison, you see TCP is connection oriented, and UDP is connectionless, which means it doesn't care. But also UDP is much faster because you don't have all that overhead of all the headers and that files in there. And that's why real-time applications and video conference are much better used for UDP. And TCP would use reliable transmission such as file transfer or banking website, depending on if you need to use TCP. So that's basically the two. Now, Telnet, it's just a service, that the application layer service, and Telnet used to be used to actually connect to routers and devices. Nowadays, we don't use Telnet. We use SSH, which is much secure. We have a public and private key between the server and the client. That is an example of explaining the two, and as you can see, I said Telnet is in plain text, so it's unsecure, and SSH is more secure in a way that you can connect and you can trust the server. So that is introduction to network technologies, and last we look at switching basics, which is how the switch operate. So the switch basically is, in the older days we used to have this little bus here, how all the devices connect to, and there was no switch involved, so you could have this whole collision domain sending packets and stuff to each other, and it was nice, but you had problems with packets because they will send packets and one will be delayed and so forth. So for that, they created the switch, and the switch basically, it's there now to basically manage traffic, let's say virtual LANs or VLANs in this case, and it's also there to detect collisions. So it's basically it has that mechanism built in to detect collisions on the network, and that's why we have the switch. Now, when we look at the layer 2 switch, a switch normally operates here at the bottom, right? So there's the layer 2 switch, and so what it does is it looks at the MAC address and the header, like I just showed you now, with the encapsulation, de-encapsulation, and that's information how it knows it needs to send it to the next particular device. The MAC address table looks like this. You have your host here, which is your IP at first and the MAC address, and you have these particular ports that's configured on the switch in order to forward traffic to the next host. And so again, on the MAC address table, it will look at the ports to determine what's the destination. So the destination will be looked at on network. What network does that PC belong to? And it will try to figure out what does that PC belong to, what IP address the PC has, and with that it will figure out what port. So in this case, MAC1 is this, and MAC2 is GO2, which means the traffic will go through this port and go out here, because that's what's known in the MAC address table that you see at the bottom. So if you look at the switch, this is a play of how it will work. So you have the switch again that looks at the destination MAC address, and also using information from the IP address also, and that's how it will determine where the packet needs to go to. The frame on layer 2. And so after it receives the data frame, it learns the source MAC address, and then it sends that accordingly based on what's in the table. So this is just an example of how the switch behaves. And here's the examples of ports on the switch. And so you will see basically it goes into these different modes: flooding, forwarding, and discarding. So basically it floods all the ports to find out what's the MAC address. Then after that, if it finds information, it then forwards it to the right port where it needs to be. And then after that, it then acts as a switch. And basically then what it will do is it will then forward the traffic. Now, what it will also do on discarding is block certain ports where it's not supposed to go out to. And so that's basically the operation of the switch. All right, so there's examples of why we need VLANs. So this is what I said earlier when we started off, that you need these VLANs to create the separation between different networks. And so there's two examples of um, A and B. So obviously B wants to say, oh, I don't want C to or A to access me, or B want me to B to access. And so you create this whole thing of VLAN technology. And so the local area VLAN is then there to create groups on the network, and then switches belong to groups, or ports on the switch belong to different groups. How it depends on how you configure it. So there again, you have an example of a VLAN. So you have VLAN 1, VLAN 2, VLAN 3, and you can see now basically the switch is configured certain ports to belong to a certain VLAN, so that certain people can't see each other on the network. So if this is HR, that is IT, and that's the data center, the VLAN 1 would only be seen would only be configured for that port, and only traffic for that port will go out to wherever it needs to go to. And so that's basically how you would do the VLAN, creating basically multiple VLANs in this case. So there, the VLAN has a frame format. So the VLAN also has a tag. And what you would do on the switch, you would create a tag, and the tag would mean that wherever that ID belongs to, so in this case, the VLAN ID is 12, in this case, 12B. It means that only if information that's sent through that VLAN will go out through that port for that particular network. So you kind of create a security feature with VLANs. So there is an example of different ways of how you can assign it. You can assign it via interface, which is you define interface, via the MAC address, via the IP and the subnet, via the protocol, and via a policy if you need a policy for your network. So there's an example of an interface VLAN assignment. So you can see the tag here is 10. And so what happens is it gets sent through from VLAN 10 here. Here's VLAN 10, and you need to configure obviously the host to obviously be on VLAN 10. So you tag them when you configure it. And so what will happen is that if you have interface for VLAN 10, it will allow it to go through, right? But it will have this here, which is called normally a trunk interface. If you didn't tag your packet that you go out, you won't be able to go out through this, and you mean you can only access VLAN 10 in this case. You can't go out. So you have to make sure that you configure the interface in that sense to be able to tag the information, or you can't obviously send out. So what I mean by this is that you look at VLAN 10 here, which is this. You send that frame. It has the layer 10, and then if it's allowed to go through and configure it as trunk, it will allow that packet to that information go through. But if not, it will block it, and it will basically say no, you can't send information out there. So that's basically switching basics. Now, when you look at VLANs, you just configure VLAN ID or VLAN paths, and that's basically the command you would do on the device on the switch. Not going to go too much with this because we're doing basics. I can't. What you can do is if you do the course, the full course, you can go into detail with this and then you really understand this much better. But what we can see here basically is that you have an access interface and a trunk interface, and you configure your ports based on that particular interface. What you want your host to do. Do you want the VLAN tag 10 to go out and then reach VLAN 20? You might not want to, so you keep that as access switches. Just only VLAN 20 tags will go to host 2 and so forth. But if you want to have the switches see each other and forward information, you would then configure one port on the switch, which is this number 3. You would configure that port and you would say configure that for trunk so that these two can see each other on the network. So there's an example of how you create a VLAN. So you have VLAN 10, you configure it, you go out, you quit it to go back to the main menu, and then you say VLAN 20, you quit, you go to the main menu, and you can also do batches also based on VLANs on that switch. Because we're talking about this switch here that we're configuring here. Okay, so that's a switch there that you're configuring. And so when we look at the other part, switch 1, as you can see there, you then basically can configure also port link access. So you're basically saying that only tags for VLAN 10 will be allowed, right? Access into the VLAN 10. So you're creating that security separation there between VLANs. There you can just configure verify the information. That's just verifying how the VLAN works. And that's it. So that is a bit. So just to recap, you basically can configure it in any way. The main thing that you want to do is you want to make sure which port are you blocking on the switch, which will obviously be configured, based on the network administrator. Right. So when we look at routing basics again is more or less understanding how the router works. So again, the router forwards information based on an IP address. But the router also has to go through a routing table, which is the routing table that you see here. And that contains the source and destination IP addresses of the next router. So that table allows the router to know how to forward information, how to stop packets from going through it, and so forth. So again, it has this table, which is called a routing table. And so what it does is it checks what's the next destination device that I need to send the information to. And with that, it knows obviously what's the neighboring router and it uses a table to determine where the packet needs to go to. So you can check the routing table also. There's a routing table with the destination and IP addresses. And then also you can have a rule forwarding also based on the router. By creating a rule, you can allow routers to perform the way they should perform. And then also you have static routes. And static routes again is more like you want to have the static route configured between two devices so that all the traffic will go on that port to that particular device that you configured and not vice versa. So that's kind of what you would do a static route for. So there's an example. So you would say IP static route and you would say the destination, and within this case, we configure RTA. So configuring this. So the destination is this one here, and the 10.0.2 is the gateway. So you configure that basically, and then the package will go straight through that based on your configured static route. Right, so there's an example of a default static route. We can see the same scenario apply as into how this works. There's another example of default route. We can see the scenario there as well. And I think that is the end of networking. So what we've basically went through is giving you a brief overview of what networking is in cloud, where you configure the switch, how you configure it so that you can have this whole thing of port control, port access, trunking of ports. And so it gets very tricky, but that's more practical. So the question here would be, we should have followed our functions of firewalls. I think it's all of them. Firewalls are there to isolate networks from different security levels. They need to do authentication, they do netting also, and they perform route calculation. So that should be all of that. And then if you look at the default routes, to question 2 are typically used at egress of an enterprise network. So you basically want to say that in an egress device, there's a device that forwards IP addresses designated for any address on the network, and that's true. So that's basically what you have your default routes for or your static routes. All right, so what we've covered is basically IP addresses. You've learned probably looking at subnetting, how why we do subnetting, what's the basic principles of network communication, which is the OSI layer, de-encapsulation, and then also some basic operations of how routers and switches operate. All right, so that covers the routing part. So let me just stop that recording also. So I'll just do this in bits and pieces.